So 4.1, linear functions. Right? They're basically starting you from the beginning of functions, and you know, Rebecca. I can see you're ready for it. So you're starting from the beginning of functions, linear functions. Who can tell me what a linear function is? Alex, please.
It's a function that goes up in a set increments. It's a straight line.
Set increments. Okay, so that's a good way of thinking. You have some points, right? And they are if you advance by the same distance, then the function advances by the same distance up here. Right? There's some sort of constancy to its rate of change, right? Okay. Can somebody give me a more maybe a more mathematical definition? Rebecca, how about you?
Does it have something to do with the set of all points?
No.
I always say that in math, so I don't know.
No. But you guys know what a linear function is. How do you describe a line? We've done it. We've already done it before, right? A linear function is a function that
One that has a slope and one
has a
has a
slope and an intercept. Right? Well, right, so it's some function that looks like this, right? Ax plus b. Right? This is a linear function. Right? So we'll try to go quickly through this since I think it's not that interesting. Or since I think people already know. A linear function. I should say that this is actually what one calls an affine function. So it's not exactly correct. If you go on into higher math, then we actually don't call such a thing linear. We call such a thing affine. But we can call it linear. It's not unreasonable to call it linear because it's line-like. So any function of the form f equals ax plus b is called a linear function. And you know, typical examples of this are linear depreciation. Okay, so this is an economic example. So usually you have something like this that, it's basically the idea that value decreases linearly. So, you know, for example, you know, in 2001, I bought a computer. The computer was about, the computer cost about $2,000, right? And then in 2006, you know, maybe the computer was worth around $300, right? And, you know, basically you assume, you probably know what this is, right? In 2001, 2006, right? Somebody says, well, how much was the computer worth at some point in between? And you assume that the decay was, the decay of the price was linear. Okay, so like to estimate the value between 2 points. And so, like, if I ask you this, well, how much did it cost in 2003, say, how would you do it? Using a linear function? Hold on, Karen. Hold on, Karen.
Oh, sorry.
Lisa, how would you?
Midpoint formula? Midpoint?
The midpoint formula? Well, let's see, this would be 2003, right? So it's not the midpoint, actually.
Or use the function of plug in 2003 to get value of y.
I'm sorry, I can't hear you.
You plug in 2003 to get your value of y, so 2003 is your value of x.
Okay, so what do you plug it into?
The equation of the line.
Right, so what's the equation of the line? You figure out the equation of the line, what's the equation of the line? You can do it. What's the slope of the line, or, yeah, what's the slope of the line say?
It's negative.
Can somebody? Okay, it's true, it's negative, but you guys can tell me a little bit more
300
precisely.
over 2,000.
It's what?
300 over 2,000.
300 over.
Oh, wait, no, it's,
Maybe I should slip, not go quicker.
no. Actually, no.
Over.
Okay, somebody tell me how to figure out this line. Okay,
1,700 over 5.
700 over 5, right? So the slope, of course, is the change in the function or the change in time, right? So it's 1,700, right? 2,000 minus 300 over 5,
Negative.
right? 5 negative.
Yeah.
And then how do we figure out the line itself? You know, Tiffany?
1 minus y squared equals r minus x minus x.
Okay, so we can use the point slope formula. That's probably the easiest since we already have the slope and we have 2 points, right? So we figured out, right, y minus 2001, say? I'm sorry, y minus y naught, which is 2000, right? So we use the point, say, 2001 from 2000, right? Y minus y naught equals slope x minus x naught,
It would be f.
right? This is the x naught, and this is the y naught. Right. So we want to do that as Elisa says, we do that at 2003, right? So y is going to be 2000 minus 1,700 over 5 times 2003 minus 2001. Right. And that's the end. Okay. 2000 minus 2 times 700 over 5. Right. So this is how you might get some guess as to what the value was at a point in between. Okay. Okay. A physical example. Velocity, right? So you have some car on a linear track, right? Right. So you have some car, and here is the so let P of t denote the position at time t. Right. Let P of t denote the position at time t. Right. Okay. Then the average velocity. Okay, so let's say that p is a linear function. So p of t is at plus b. So right. So like the car, the p of t is the distance, is the position on this number line. So the car is just going backwards, forwards, and forwards on a straight line. Right. The average velocity of the car is going to be the change in position over the change in time. Right. Change in position over the change in time. So if I ask you, so here's the question, between time A and time B, what's the average velocity? What's the average velocity? Oh, that's well, it would be the change in p or the change in time, right?
So it would be, I'm not sure the position would be, but the overtime would be a minus b.
Okay, well, b minus a is actually obvious, but it doesn't matter. Right? So the change in position or the change in time, right? So the change in position is just going to be the difference of the two positions, right? So p of b minus p of a.
Right, yeah.
Okay, and what does that turn out to be? Julian, what's p of b? If our car is the linear car, we have a car, it's called a linear car because it moves like a line. So p of b is just plug it in.
AB plus B.
And ab plus b, a will be minus b. P of a is
2 plus B?
Yes.
Or
no. Okay, so capital A and little a are different.
A.
A times little a plus b. They're not the same thing. It would be minus a. Okay. Right, and who knows what that works out to already? Is it? Yes, it works out to A, big A, yes. Right, because you get AB plus B minus AA minus B. So the B's cancel off, right? And you get A times B minus A over B minus A. Right? Those guys cancel off. Okay. So what this tells you is that a linear function is something that has constant average velocity. So point of this example is that any linear function, if it's a linear function, then it has constant average velocity. That is, if you're riding this car, it would be traveling at a constant speed. Right? Over any interval, if you took the average velocity, you get the same velocity. Okay, so let me do what will probably be, so the homework problems in the section are basically of the following sort. Let's say something like this: you have some car, you have car A, whose position is 3t plus 100, 3t plus 100, and you have some other car B, whose position is 20t minus 36. Okay. And they ask which car is faster. Okay. Which car is faster? Right. Well, you look at it, right? Which car is faster?
Overall, like in a longer distance.
Not in a longer distance. These cars are linear cars, so their speeds are constant.
B.
B.
So that's a higher.
Because B's got the fastest leg. Right. So B. Right. You don't need to even think about that one. Right. Just look at it. You don't need to work out anything. You just catch it. You just look at it. Which is ahead at time 0. Again, it's just something you look at. Which is it? A, right? Because at time 0, A is at 0.100, and B is 36 units behind the beginning of the race. Okay. And then the question is, when does B catch up to A?
Use graphs.
You can do it. You can do it. You just set the two equal to each other, right? You just say, at what time, when you translate this, right? You translate this question. For what this question, if you translate it into math, is at what t does the position of A equal the position of B, right? Okay, so that's at what t does, for what t is 3t plus 100 equal to 20t plus minus 36. Hmm?
And then you just solve for t.
And you just solve for t, right? So it's easy, right? You subtract 3t from both sides, right? You add 36 to the other side, right? You get t is 136 over 17. Right? Okay. Okay. Okay, everyone close your eyes for a second. Should I go faster? Raise your finger. Slower? Raise your finger. Just wait. Raise your finger. Okay. Hands up. Okay, clap hands up. Okay. So there's some people who think this is about the right speed. I don't need to go any faster. There's a fair number who think this is the right speed. So we're just going to keep it this pace. Okay, the last and most important idea is, most important example is something called linear regression. Okay, this is something that we use in science. So this one actually is interesting and important. So it's like this. You have some data. Okay, and your data is roughly line-like. So you have data roughly line-like, right? And you want to express this using some line. Okay. Okay. So what line do you choose, right? What line does one choose?
You choose.
What do you choose, Alex? Maybe you know.
I mean, I keep on my calculator, but you just choose the line that kind of, like, I guess simply put, that goes through, like, the most of the points, or between most of the points, so it's closest to all of them altogether.
It's closest to all of them altogether. So the closest line, right?
Yeah.
Right? But then the question is, what do you mean by the closest? What's the distance between a line and the points? How do you measure that distance? What do you mean by closest?
It's gonna, like, it's like the line that can, like, be closest, like, if you average it out, that is closest to all the points.
Okay,
So it'll run, like, roughly between all of those.
okay, so I think what you're saying is that you choose the line and you look at maybe the distance between the point and the guess point of the line,
Yeah.
right? You look at these distances here and you say, I want the line that makes the sum of these distances the smallest,
Yeah.
right?
Yes.
Maybe that would certainly say maybe closest means, so you take this line, okay, let me call this line L, okay, and you have all these points, let's call these points, these data points, I'm going to call them x1, y1, x2, y2, xn, yn. So I've got n points. Okay. And let's say that we're going to say closest means that I'm going to take I should say this is not quite right, but it's a good guess. Okay. Closest means to Alex that you take the line and you evaluate it at x1 and you look at the difference between that and y1. Right? You look at the distance between that and y1. That's this distance right here. Does that make sense? Everyone following? Right? You take that distance, right? Because you take L, here is x1, you take L of x1. This point is x1 and y1, right? So you take L of x1, and you look at the difference between L of x1 and y1. You take the absolute values, so you get some positive number. Okay. So we take that, and we add the next guy's error, the next guy's error, all the way to the last guy's error. Okay. And you try to, closest means to make this thing small. Okay, and the line that makes that thing the smallest, that's what we're going to use as our approximation line. Okay, that is a great idea. That is a great idea. That's not what's called the line of regression, but it's actually related to the line of regression. Okay. So let me tell you what people use in science. Rather, they take the line that closest means closest in the least squares sense, right? In the least square sense, and this is the sense that is important to us. Closest in the least square sense means to take these things and square them. And you make all those things small. Okay. So you look for the line that makes the sum of these squares as small as possible. You want the least squares. Okay. The least squares. You take a line and you look at this least squares error, which is the sum of all these areas here. If I make squares out of these differences. Okay. You take all these squares, you add them together. This thing is called the least squares, the square errors. Right? And you try to find the line that has the least squares error. Okay, and that line is called the line of regression. Okay, and that's the line that people use in science when they're approximating the line, approximating roughly linear data. So the question, of course, is what's the question?
What's the line?
How do you find that line? Right? How do you find that line? How does one find that line that minimizes this error? And the answer is that basically you can't do it at this point. Okay, you can't do it at this point. You need to have a little bit of calculus. I mean, there's sort of a tricky way to do it without using calculus, but it's sort of like basically the best thing to do is wait until you get a little bit of calculus, and then you can do it easily.
You can just use your calculator.
No. You can. Okay. So yeah, that's what you're doing in science for sure. But calculus, as we were starting to see. Starting to note is that it's about finding the place where something is smallest, finding the place where something is biggest, right? Here we've got this error thing, and we'll be able to use calculus to say where is the error smallest, and it'll pop out an answer. And say, oh, that's how I get my line. And that will have to do with the notion of average velocity taken over increasingly small distances. This is about instantaneous velocity. That's basically the key to optimizing this way. Okay. Okay. So okay, let's go on. So lines, you know about lines. Second section, quadratic functions. Again, something that you know about 4.2. Quadratic functions, right? So, right. So your data, of course, might not look like a line. right? If your data looks like this, then to approximate with a line is silly, right? Instead, you want to maybe approximate with a quadratic function. And so let's just sort of review a little bit, about quadratic functions. So just like a little bit of review. Basically, to answer the following question, how does one determine the, for example, the vertex, right? If you have some quadratic function, how do you determine where the vertex lies? The vertex, the axis of symmetry. Well, I guess if you have the vertex, you already know the axis of symmetry. The extreme value. I guess if you have the vertex, you already know the extreme value. And if it's up or down. And if it's up or down. If it's going up or if it's going down. For quadratic functions. And the trick to understand quadratic functions is basically just completing the square. So let me do an example or two, and that would, I think, make it clear how to understand the behavior of a quadratic function. So here's an example. F of x is 3x squared minus 6x plus 3. Okay, well I guess, in fact, in this one, not even use completing the square. Maybe I should change it a little bit. So I do, I make 6x plus 6, okay? 3x squared plus minus 6x plus 6. Okay, so I want to make this thing look like a square. Maybe the first thing I'm going to do is to factor out 3. So I've got x squared minus 2x plus 2. Yeah, plus.
So is the reason we're completing the square for this one because you can't easily factor the zeros, like in the previous example where it was 3, you just find the zeros and put in the middle.
Right,
Zeros.
right.
So, but we complete the square because we can't do that.
I mean, you could find the zero some other way.
Right.
And then take the average.
Okay. So how do you know when to escape?
It's up to you. I think it's sort of like, either way is pretty easy.
Okay.
Either way is pretty easy. If they ask you to do completing the square, then please just make completing the square. Okay, so what do you do to complete the square here? Okay.
You take half the -2 and add it.
Okay, take half the -2 and add it on.
Oh, sorry, square, yeah. Square.
Square it. Okay, so you get half the -2 is -1. You square it, you add that thing on. Okay. And as I said before, you sort of have to subtract. You can't just you have to compensate for having added that thing on. And so what we end up with? We end up with 3 x minus 1 squared plus 1. Okay. And just to make this a little bit easier for me to understand, I'm going to write it like this. 3 x minus 1 squared, I'm going to pull the 1 outside. You don't have to. But to me that makes it easier. Yeah, Carolyn.
And it's 3 because it's the 1 and the 3, so you multiply by everything.
Yeah. The 3 distributes across.
No, that's what
No, it's fine. Okay. So then we have all the information we want about this thing, right? What's the axis of symmetry for this function? where about what line is it symmetric? About what line is it symmetric? Where is the vertex?
X equals 3.
Okay, let's think about it this way. Here we have the function y equals x squared, g of x equals x squared. What's the graph of this thing? How do we get the graph of f from the graph of g? Well, right.
So it would be shifted to the right 1 and up 3.
Okay, we shift it to the right one. We multiply it by 3, so we have to sort of stretch it when we multiply it by 3. Because every y value gets tripled. Okay. And then we move it up by 3. Okay, so 1, 2, 3. To here, we get a stretched guy. Okay, so here was 1. Okay. And what we see is that the vertex, right? The vertex, well, I mean, immediately the axis of symmetry is x equals 1, right? The vertex, well, it's 1, 3, right? It has a minimum value, right? You see it has a minimum value is 3 at x equals 1, right? That's where the vertex is. Right. And we see that it's going upwards. We know it's going upwards because we're multiplying here by a positive number. Right? We've got the x squared guy, we multiply by a positive number, so it's going to be, it doesn't change, multiplying by a positive number, it doesn't flip it over. Okay? Multiplying by negative, it will flip it over. So we actually could have seen that from here. We actually could have seen some of that from here. Like the axis of symmetry, you see that it's basically around 1, right? Right? Because when x equals 1, we get 0 here, right? And then if we move a little bit to the right of 1 or a little to the left of 1, the same thing happens, right? If I go to 1.5, what is x minus 1 squared? If I go to 1.5, what's x minus 1 squared? Well, it's going to be a quarter, right? A half squared. If I went, so that was at 1.5. If I went back to 0.5, what's x minus 1 squared? It's again a quarter, right? If I go a little bit to the right, I get some value. If I go a little bit to the left, that same distance, I get the same value, right? This thing is symmetric about the line x equals 1. Just look at it, right? If you understand the square, then you see that that's what happens. So the axis of symmetry is obvious from this point, right? That it's symmetric around 1, and then to get the vertex, you would just plug in 1, right? You get 3, so 1, 3. Right? So in some sense, you don't need to go back to the translation stuff, but if you don't understand the graph, don't understand the function, then you can. Okay. Okay. So to give you an example of a tricky problem, here it is. F of x is x squared, square root of x squared minus 6x plus 73. And I ask, what is the minimum value? What is the minimum value? Who has an idea of how to do this? I mean, you could, but maybe let's do it in a way that's more connected to what we just did. Lauren?
So could you complete a square of what's under the square root and then find, like, basically just what we did? You just have to remember that it's the square root.
Yeah. So the point is that to find the minimum value of this guy, well, let's just find the minimum value of this, right? Because wherever this guy reaches its minimum value, the square root of it's going to reach its minimum value, right? The smallest value we get out of here, well, we take the square root of that, and that will be the minimum value here. Okay? So just, it looks sort of tricky, but it's not, right? Just find the minimum value for the thing that you're taking the square root of, right? Which we can do since we just saw how to do it. Right? Somebody tell me how to do it. Well, you get, what do you do?
I'd like to do the square.
Yes, so that's 9. Right? So add 9, subtract 9. Right? The thing that we get, this thing is this, which is x minus 3 squared plus 64. Right? So what's the minimum value of this guy? Of this guy? 64. Right? The minimum value of this guy is 64. And when we take the square root, we get 8. Right? So this obtains its min value at x equals 3. Minimum value of 64 at x equals 3. Right? So f obtains its min value at, again, x equals 3, and you get root 64. That is the same.
Why is it 3 instead? I thought you would just square root of 64.
It attains it when x equals 3. Right? When x equals 3,
Oh.
you get 64. Okay, that's it for today. And I promise it'll get